next, like I made it due 1 week from today for 6-2 and 6-3. And for 6-1, although your Alex is due right before class next Tuesday, but for 6-1, I made that due also next Tuesday, and you can choose any 5 of the 7 problems and submit those. If you do all of them, great. I mean, I grade homework based on completion because I never want, it's not fair if you do your homework that you like get a 0 or something, if you didn't get it right. The point is to learn, and, that's what homework is about. So just if you completed it, that's like, I am lenient on the grades. Maybe I'll make comments if I have time, or if I see something really wrong, I'll put a comment there for you. But otherwise, you guys can now submit those book problems. Alex should be good, and the due dates should be correct. So if you do have any other questions about that, please just let me know.
Thank you for doing it.
Yeah, thank you guys. Thanks for reminding me. I thought I was on top of it, but I am, in terms of exams and reviews, and I am kind of on top of it, I'll say. Okay, so let me share my screen here. Today we are covering 6.2 and 6.3 together. I do have to leave about like 5 minutes early. So, we should still have plenty of time, we should be able to finish, no problem. But I just wanted to let everyone know. So class will end at least by 7:40 tonight. Now I remembered to flip this, and I'm going to, give me a moment.
Recording in progress.
All right, so I have the chat up. I see some faces. It's great. So again, welcome everyone that I haven't talked to just yet. Today we are going to be doing 6-2 and 6-3. 2 little announcements. One is that you can see here, I am posting a quiz. It is on material that was actually from last week, I believe. I'm opening it tonight. So I did say I'm ending class about 5 minutes early. I am going to open it at the end of class, probably around 7:30 though. And then so if you want to do it tonight and you don't have time this weekend, you can get it done tonight or tomorrow. And then I made it due Sunday. So if you do not have time, I mean, I get it. My life is absolute chaos right now. So are all of our lives, right? And every day is different. So, oh yeah, perfect. And Joseph does, so for Adrian, I am not, so ACC, this class is supposed to be live. So I do not post recordings or share recordings, but ACC just records all of and I just let it record, right? Yeah, so I do not post them, but Veronica did say Joseph posts those to the GroupMe. So if you're part of that, you'll see these recordings there. And I also will post the notes, right? And I'll leave all of this that you're seeing here. I'll post those tonight. If it doesn't happen right after class, it will happen late night. And so, I gave you guys time for your quiz. It's a short quiz. Don't let it stress you out, because I know you have book problems, and I really should have planned a quiz when you don't have extra book problems. But the next unit, I can promise you're going to have a break where you're just doing Alex homework for 2 weeks, and there's nothing to submit online, and then there's an exam. So you will catch a break later, and maybe I'm making it crazy for you now. And yeah, so if someone has the GroupMe link, feel free to send that in the chat. Oh yeah, Michael.
I was just curious if that, I didn't ask for the closed captions, but did that work?
Oh, is it working? So I know Jakob suggested it.
Yeah, it is work.
Okay, so it's working. So
Okay.
that's good.
Okay.
Yeah, so it's working. So I guess if you want to request it, you should be able to do so on Zoom, I'm pretty sure. Okay. Yeah, so I'm glad we were able to figure that out too. So for those of you that, you're in a place where it's really crowded or noisy, hopefully I will speak slow enough that you can read what I'm saying, and I will speak clearly so that it can read my words correctly. But so let's get started on 6.2 and 6.3. I guess the other thing I did say, but I didn't write it. is that the book problems for 6.1 and then 6.2 and 6.3. So I did change it so that for 6.1, you can submit, for 6.1, you can submit, for 6.1, you can submit any 5 of the 7, right? Choose 5 of the 7. You don't need to do all of them because that was a lot. And then 6.2 and 6.3, submit them together. It's 2 problems per section. And for this, I extended this to be due next Thursday since I did not make this available. And 6.1, I just made it available due next Tuesday. So, and Tuesday evening. So you could even do it, I think, during class, but get Alex done for 6.1, 2, and 3 before class on Tuesday. Okay. And if you need extensions or need anything, please just email me. And if something comes up, I understand. So just let me know. Okay. So today we're kind of talking about more exciting formulas, I guess, sum and difference formulas with sine and cosine. So there's this little trick that we can do, or maybe not so little. And when we have sine of like u plus v or u minus v, right? Or even cosine of u plus v and u minus v, we can actually rewrite this as in terms of what you see here. So in terms of the sines and cosines, so this product can be written as a sum of these products here. And the cool thing is that we might know what the sine and cosine of u and v are, but not when you add it together. So you'll see a bunch of examples today and we'll discuss this. And so we will talk about a little tip or trick on how to remember this, but you can see here that sine of u plus v is going to be sine u cosine v plus cosine u sine v. So you're swapping the trig functions and then adding, right? And then for subtraction, it's exactly the same thing, but you are subtracting, which, okay, that makes sense, makes me kind of happy, right? For cosine, the nice thing, and remember, it's an even function, maybe this will help. So we actually do cosine of both angles minus sine of both angles, and notice that these signs here are opposite, but the function is the same, right? Cosine, cosine, sine, sine, and these signs are opposite. Whereas in the first one, these signs stay the same, but they alternate in terms of, sine times cosine plus cosine times sine. So again, we'll look more at this and try to come up with little tips or tricks, or just rewriting it over and over is also going to help you remember. So our known angles and degrees. So first, the reason we're writing known angles and degrees and known angles and radians is because these are the angles that we want our u and v to be, because then we know what they are and we don't need decimals. We'll have nice fractions or, radicals or something like this. So in degrees, we know 0 degrees, right? We know 30, we know 45, we know 60, and we know 90. And I'm just going to do the first quadrant. I'll focus on that, right? So we know more, but this is the first quadrant. And then just translating that to radians, just a little reminder here, 0 radians. Then we'd have pi over 6, which is 30 degrees, pi over 4, pi over 3, and pi over 2, right? Now, keep in mind, if you want to write these, say in terms of, if you have like 5 pi over 6 or something, and you want to write all of them in terms of pi over 6, like you can kind of change, 2 pi over 3, or pi over 3 is like 2 pi over 6. So if you needed that, you could do that. But we'll talk more about that when we see some examples. So let's tackle number 1. Right? We want to use addition or subtraction to find the exact value. So sine of 15, I mean, sure, you could put that in your calculator. Maybe you could figure it out from there, but it's going to be much easier by using this addition or subtraction. So for 15, I think about the the reason we wrote these known angles is because 15 degrees, we want to find two numbers in our known angles that either subtract or add to be 15, right? In this case, subtraction is going to be a little bit easier. Yeah, exactly, Jakob, 45 minus 30. And you could do 60 minus 45, like you know, there's different, but we're going to do 45 minus 30. So I have sine of 45 degrees minus 30 degrees. And now I reference my function up here, my equation up here, sine of u minus v. So notice now my u is 45, my v is 30 from this equation here. And so I'm going to rewrite it, and I can say, okay, this equals sine of 45 times cosine of 30 minus, remember the sign stays the same here, then cosine of 45, and then sine of 30. And now we can use our little unit circle, right triangle trig knowledge that we've remembered, right? And we can just plug these values in that we know. So I know sine and cosine of 45 is root 2 over 2. So I'll put it below. So I have root 2 over 2, right? And then we have values here that we need to figure out. So I remember cosine of 30, this one is the 30 is pi over 6. This is root 3 over 2. It should be, I believe. If I'm wrong, please interject. And then that means sine of 30 is the opposite one. It's 1/2, okay? And so now this isn't going to look really nice, but we're going to make this, you know, pretty nice and exact. So no decimals. So now I have square root of 3 times square root of 2 is square root of 6 over 4 minus square root of 2 over 4. And I want to write it all as one fraction. I don't want to have two fractions, and we have the same denominator, so it's not too hard. So this is actually going to be square root of 6 minus square root of 2. You can't simplify that at all, over 4. And this is sine of 15, right? So that's pretty cool that we were able to use this equation for part A, the sine of u minus v. And now for part B, I have cosine of negative pi over 12. So this is where I look at my known angles in radians. And I have pi over 12. So it might help. I'm going to do this, but you don't need to because you might figure it out right away. But it might help if I rewrite all of these in terms of twelfths. So pi over 6 is 2 pi over 12. Then we have 3 pi over 12. Then 4 pi over 12. And then 6 pi over 12, and etc. Right? So these are the known pi over 12, or, you know, twelfths in radians. And so if I just want to get 1 pi over 12, I could take, okay, I could do, oh, did I do this right? 3 pi over 12 minus 2 pi over 12, or 4 pi over 12 minus 3 pi over 12. Whatever, you know, whatever your heart desires here. Oh, except I want negative, don't I? Yeah, okay. So I want negative pi over 12. So I'm not going to do 3 pi minus 2. I'm going to do the smaller one first. So maybe I'll do 3 pi over 12 minus 4 pi over 12, right? Or you could do 2 pi over 12 minus 3 pi over 12. Whichever one works for you. But we're going to start with the 3 pi over 12. So this is going to be cosine of 3 pi over 12 minus 4 pi over 12. And I'm writing it like this. I'll change it, or we can change it back to the normal fractions that we know, but I'm writing it over 12 so that we can clearly see that this equals, you know, when I subtract these, it equals negative pi over 12, and I'm good to go. So now this is nice because I can, well, if I just rewrite it one more time in my regular, so 3 pi over 12 is pi over 4, and 4 pi over 12 is pi over 3. So now I'm looking at cosine of pi over 4 minus pi over 3. And for this guy, I'm going to use cosine u minus v So I'm going to apply this here, right? And now I'm going to say, okay, so this is going to be cosine of pi over 4 times, times cosine of pi over 3. So first we take cosine of both angles, but then we do the opposite sign, so plus instead of minus. And then we have sine of pi over 4 times sine of pi over 3. And again, if you need to draw your unit circle and say, okay, you know, pi over 4 and, okay, well, maybe I shouldn't do that one. But if you need to draw your unit circle and maybe have pi over 3, you know, some wherever, like say this was pi over 3, and you need to think about like, what is that point? Feel free to do that, right? Like write a little scratch work. And I remember, I'm sorry, I wasn't showing scratch work for part A, but if you want to do that, feel free. And then, you know, if you wanted to also draw in, okay, like if the green was pi over 4, then you know that point is root 2 over 2, root 2 over 2, right? That one's kind of easier, so I wasn't going to write it, but you can write this in because then it's really easy for you to see the sine goes with the y, the cosine goes with the x, and you have your points here. So let's fill that in. So for pi over 4, it's root 2 over 2, right? For cosine of pi over 3, and remember I wrote it over, I wrote it right here. So cosine is x, so this is 1/2. Then I have plus sine of pi over 4, so root 2 over 2, times sine of pi over 3, which is root 3 over 2. And very similar to the other one, I get square root of 2 over 4 plus square root of 6 over 4. And we want to just write this as one nice fraction. So I'm going to write square root of 2 plus square root of 6 all divided by 4. Oh, I'll move this. So hopefully that's making sense. Now that's to me, this is like the more useful way to use these formulas. However, looking at part C, I can see I have sine 65 cosine 20 minus cosine 65 sine 20. So I don't know, like sine and cosine of 65 or 20, that's weird, but we can rewrite this and we can say, okay, here's my U, here's my V. I see sine cosine minus cosine sine. So if you look above, I know the alternating is going to give me sine, and then like the alternating like sine times cosine, and then it's minus in the middle. So I'm pretty sure it's also minus in the inside. So this is actually going to equal sine of U minus V. So 65 minus 20, which, I mean, lucky us, right? They do this on purpose, but this is going to equal sine of 45 degrees. And that we don't have to think much about because we already know that's square root of 2 over 2. And so this whole complicated, you know, formula or expression is just square root of 2 over 2. And the whole point of these sum and difference is really just to get exact values. Because when we have square roots and we have long decimals or irrational numbers or something, it can be pretty frustrating if you want like to be precise. And so these get us just exact values. Right? And so like in number 2, we're asked to find the exact value of cosine of alpha minus beta, given that, okay, here's some fun stuff. Given that sine of alpha is negative 2/5. So they drew these pictures for us, right? So alpha is this first one. And we know that it's 2 down. Like if we make the triangle, it's got to be over here because it's opposite over hypotenuse and the opposite is 2. The hypotenuse is 5. Oh. In the example B, so in part B, do you need to apply even odd rules? So there's a question that from part B here. No, you do not need to apply even odd. We made this equal to negative pi over 12, although it would have been the same thing, right? Because cosine is even, you would have ended up with square root of 6 plus square root of 2 over 4. Same, right? And we can change that order because it ends up being in our answer. It ends up being addition here, right? And so if these were just switched, then it wouldn't be a big deal. But that is a really good question. You could apply that. We did not, though.
Okay.
Yeah, we did not, but you definitely could. Okay. So back to our right triangle here. So we have 2 and 5, and we could find this if we need it. I'm not sure yet, right? This, maybe I'll call it something like A, like little a. And then, and it tells us alpha's in quadrant 4. Okay. And then tangent of beta is this for beta in quadrant 2. So then we knew that, beta had to be coming here, and we make a right triangle, and they gave us opposite over adjacent, and maybe we call this C. So what we want to do, we want to find the exact value of cosine alpha minus beta. So first I'm going to write this as a formula to see what we need. And if we need to find A and C, we probably do, but I just want to see the formula first. So cosine alpha minus beta, think of this as U and V, right? So alpha is U, beta is V. And again, I can go up. I mean, I don't like scrolling so much, but just so we see, I'm looking at cosine U minus V, and that's what I'm going to use. So I'm going to say this is cosine alpha, cosine beta, plus sine alpha, sine beta. And you might still be thinking, okay, what the heck? We don't know any of these. But this time, instead of using our unit circle and our little knowledge of sine and cosine there, we're going to use SOHCAHTOA, which I really should have started class with that song. I wanted to so bad. In office hours, I almost pulled it up, but I did not. So we're using our SOHCAHTOA here. And this means we do need to get the sides A and C. So you can just do a little bit of quick right triangle trig. So for this guy here, you can do 2 squared plus A, or A squared plus 2 squared, whichever, equals 5 squared. And so then you get A squared equals 25 minus 4, so 21. And then A is square root of 21. So this guy is square root of 21. And we'll just leave it like that. No need to simplify more. Well, that would be a decimal. And then for the next one, it's 12 squared plus 5 squared equals C squared. So we get 144 plus 25, which is 169, I believe. And that's C squared. Yeah, so this works out nice. This is going to be 13 is C. So this is 13. Okay, so now that we have all of these, right, we can actually, think of, so we really only need SOHCAHTOA. There's no TOA here, right? So for cosine of alpha, so now I first focus on alpha. I'll highlight the cosines. I focused, oh my gosh, I'm sorry. That. I focus on my alpha triangle, which is here for my cosines. I'm actually not even saying that right. Just for the alphas, I focus on this guy, this triangle here. And then for the betas, I'll focus on this triangle here, right? Okay, now that's right. So cosine of alpha is adjacent, so square root of 21 over hypotenuse, so 5. Cosine of beta, going to the green triangle, is 5 over 13. Then I have plus sine. Well, they did, we have to remember, which, I mean, I'm being really bad here. We have to remember the 5 is negative, because they told us that based on where we are here. And the 2 is negative here, technically, right? Because of which quadrants we're in. So this 5 needs a negative with it. And then for sine of alpha, we have a negative 2/5. And then sine of beta, it's positive 12/13. Okay, so now we can just write, we have negative 5 square root of 21 minus, because minus 2 times 12, so minus 24. And then all divided by 5 times 13, which I think it's 65. Yeah. So I'm writing it all as one fraction first. If you need to see it as 2 fractions, write it out separately. I just kind of ran out of room, so I was being a little bit lazy there, but this would be your final answer. Okay, so now that we've seen some examples and different kinds of ways we can use these identities, we're going to talk, I mean, we already have a little, but we're talking about tips for memorizing. So, oh, and if I'm going too quickly, please just stop me. So tips for memorizing. Well, what we said before with sine, so these guys here, it's always sine, cosine, cosine, sine, right? And with cosine, so that's with sine. And with cosine, it's always the same, cosine, cosine, sine, sine. And each of them, they start, you can see that each of them start with the same, like if we're talking about sine, they start with sine. And you know that this one will alternate to the other trig function and then do it again. Whereas the cosine, starts with cosine and it stays the same, then it takes the sines. Now you're always doing the opposite angles. So you're always doing u and then v and plus u and then v. And like I said before, for sine, let's do these, maybe we'll do green for stays the same, and these ones are going to change, right? They'll switch. So now we can write these out. So we'll get sine of u plus v should be sine u cosine v. Sine stays the same, so plus cosine u sine v. Right? And we always, and based on this, it's always, oh my goodness, nothing likes me today. It's always u and then v, like whichever, it's always the first angle and then the second angle, right? So for sine of u minus v, we'll get sine u cosine v minus cosine u sine v, right? And again, this is also just to help you, we're rewriting it, but hopefully it kind of helps you see it a little as well. So for the cosine, when we switch, remember we get the same, like cosine, cosine, sine, sine, and this red highlight, I'm saying that means that the sign in between is going to be the opposite. And Jakob asked, do you see tangent? So tangent is sine over cosine. So you could do this for tangent, but you would convert it to sine and cosine. There's no, at least for, there's no sum or difference for just tangent. And we're not going to see it if that's what you're asking. Okay, so we have cosine u cosine v minus sine u sine v, because it's the opposite sign and I'm going u and v. So then I have cosine u cosine v plus sine u sine v.
So we don't use the tangent for the.
No, we're not. I mean, you, like I said, you can use, like if you were given tangent, you would convert it, it's sine over cosine. So you would end up using the sine and cosine sum and difference formulas, if that makes
I
sense.
don't know, the book has a formula like tangent u and plus tangent v, and all over 1 minus tangent u tangent v.
Right. And that comes from the sines and the cosines. So
Mhm.
well, at least for now, we're not doing that in this, we're not going to do the tangent formulas,
Right.
although it exists, right?
Okay.
But it comes from sine and cosine. So later, if we see any examples with tangent, we're actually just going to make them sine and cosine. We're not going to have to, because we're also not going to memorize that formula. Yeah. But in calculus, this might be more relevant or like later, right? And so the textbook will show it. I do wonder if you have homework on it though, but it's not in the notes. So I feel like we shouldn't have assigned that for the homework. If we did, feel free to like email me and, because I can talk about it or find out like why that is, like, or let them know so that, they know that the note, what's in the homework, it's not even close to what's in the notes. Okay, so now we're going to use these to verify this identity. So remember before how we verified, and we always start with the left-hand side, we do some work, and then we get that it equals the right-hand side. That's the goal, right? So let's do that. So this is my left-hand side. So I'm going to start, my left-hand side is, and think of this as your U and this as your V, right? So I'm going to have sine of X, and it's minus here. So I'm going to have sine of X cosine 3 pi over 2 minus cosine of X sine of 3 pi over 2, right? And now I want to figure out what this is. So I don't know sine and cosine of X. That's the whole point. We're just verifying. But I do know cosine and sine of 3 pi over 2. And if you remember, if you want to, look at it on your unit circle, it's 0, pi over 2, pi. 3 pi over 2 is here. Okay. So 3 pi over 2 is here. And so this point is 0, negative 1. So my cosine is 0 and my sine is negative 1. So this equals 0 and this equals negative 1. So now I can rewrite this, and this is just sine of X times 0 minus cosine of X times negative 1. And so this goes away, it's just 0. And then the negatives cancel each other out over here, and we get a negative times a negative. So we just get that this equals cosine of X, which this is the right-hand side. So we verified because it's cosine of X here, and we're happy. And now I see something. I think this looks a little more complicated, but let's see. We have just cosine of X plus Y and cosine of X minus Y. So we have to use both of these formulas up above, right? We're going to use both of them. And so the first one, and remember it's cosine, cosine, sine, sine, and it's the opposite of whatever you see in here. So for this first one, I'm going to get my left-hand side. I'm going to get cosine X, cosine Y minus sine X, sine Y. That's that first. So this whole thing, like this whole thing represents just cosine X plus Y. Then I have minus, and then I'm going to get this. Ooh, that's not what I wanted. And then I'm going to get the next cosine of X minus Y. So cosine X, cosine Y plus sine X, sine Y. Right? And this whole parentheses represents this right here. So now I can figure out, okay, what's going on. I'll rewrite this just for everybody who wants all of the work here. But you could just distribute and kind of simplify yourself. But this first part stays the same. Then I'm distributing this negative into these. So minus cosine X, cosine Y minus sine X, sine Y. Okay, so then from here, I can see that this whole term and this whole term, they cancel, right? So this whole term, cancel each other out. And I'm left with -1 times this and -1 times that. So -2 sine x sine y. So this equals -2 sine x sine y. And this is the right-hand side as desired, right? So we're feeling good again. So let's see if part C can trip us up. And I think maybe this is where Jakob's question comes into play, but we are not going to be doing anything with the tangents here, but I see a tangent. So maybe this is scary, but we'll handle it. So the first thing that we're going to do is just change, we start by this is the sum and difference formula that we can change. And then we'll go from there. Then we can probably simplify and do some things. So we're going to start with the whole, and we always start with the whole left-hand side, right? So my left-hand side, so I'm going to, that sine of x plus y, so that's going to be sine x cosine y plus, because they're both plus, they match each other. And then we have cosine x sine y. We swap the sine and cosine. And this is all divided by cosine x cosine y. Okay, so the nice thing about this is that it looks like some things will cancel, but I'm going to rewrite it a little bit. So I'm going to write it, although we love one fraction together, I'm going to write it as two fractions so you can clearly see what's going on. And then we'll hopefully get what's on the right-hand side. So I see sine x cosine y over cosine x cosine y plus cosine x sine y over cosine x cosine y. Okay, so again, I just separated it, and there is like a heart method if people like where you take this and then you add this. I mean, that's supposed to be like a heart method, but this fraction's a bit messy. So that's what I did there. And now I can see these just become 1 and these just become 1. So I'm left with something fairly simple. I'm left with sine over cosine x and sine y over cosine y. And I know that sine over cosine is tangent, right? So this is where I can say, okay, this equals tangent of x plus tangent of y. And this is my right-hand side. Okay, so hopefully that has us feeling good about the sum and difference formulas, because those are all the examples you should see. Your textbook will get more complicated. And like Jakob said, there's going to be tangent in there. So if you explore the textbook and you're really curious, I mean, that's great. But I can tell you that it will not be on an exam or anything like that. And if there are ALEKS problems in your homework that involve the stuff from the textbook, I mean, just let me know. But feel free to Google it and try to get use the example and work through it that way. Because you should still know how to do it. Like it's going to be very similar to what we're doing now. However, you won't see it on like a test or a quiz or anything, at least for this course.
Could you re-explain the heart method that you just used?
Oh, yeah. So again, my fractions just not pretty. I'll rewrite a different one just to show you. So if I have something like 5 plus 6 all divided by 18 or something, and I wanted to write it as two separate fractions, then what I would do is I would take 5 over 18 plus 6 over 18, and that's what this equals. This is 5 over 18 plus 6 over 18, right? Now, does that make sense? So now
Yeah.
It was weird when it was like this whole thing, like it was less heart shaped and more like weird, I don't know, paddle boards crossing. I don't know. But yeah, so hopefully that makes sense.
Cool, thank you.
Yeah. And I'll kind of, I'll keep this here, but I'll block this off. Like this is an aside and it's unrelated. So Okay. All right, so now, so the reason I'm saying the whole sum and difference formula, hopefully you're feeling good, because now we look at the next part of these, like this is probably 6-3. We look at double and half angle formulas. And again, we're only gonna focus on sine and cosine, at least, I mean, the formulas, although there might be a formula or there is for tangent, cotangent, secant, cosecant, we're just always going to come back to sine and cosine for this class. But know that, I mean, there's always kind of more out there, right? Okay, so now we have these double angle formulas. So how exciting. What this means is that when you have sine of 2 theta or cosine of 2 theta, or even, okay, tangent of 2 theta, we can apply the sum and difference formulas and then kind of manipulate it and write something nice. Or maybe it's not nice, but sometimes it really helps to solve a problem, to split something up or bring something together and have just sine of 2 theta instead of this whole long thing. So let's take a look. So sine of 2 theta is, and this is not really anything new, but like we're showing you in this, like in some courses, they give you the formula and they say, here's the formula, you know, memorize it, have fun. In this course, we have done a lot of like, how did we get this formula? Where does this come from? And even if you don't feel that way, that's how everything is presented to you, right? So in this case, sine of 2 theta, we're not giving you a new formula. We're actually saying, okay, look at that sum formula from above, and what would it be if it was sine of theta plus theta? So this would actually be sine theta cosine theta, right? You start sine cosine, you keep the plus, and then cosine theta sine theta, right? And what's really going to blow your mind here is that, well, the nice thing is that this is just 2 sine theta cosine theta, right? Because we can multiply sine or cosine first. It doesn't matter. So this is just 2 times sine cosine. So the nice thing is then, I mean, you can see this, or maybe I'll do this down here. And so the main formula, so we're just describing how we get this, but the formula is sine of 2 theta equals 2 sine theta cosine theta. And a lot of times you don't know, a lot of times, I mean, even when I definitely, the first time I learned this, I was like, all right, memorize those formulas, don't care, next, what's going on. But really knowing where it comes from is so interesting, or at least to me, but I think it's an important part of learning it, and you remember it a little bit better. I just know that when I learned this stuff the first time, granted, I probably learned it like 10 times, over and then teach it. But learning it the first time, I just kind of thought, okay, like maybe I need to know how to derive it, but really I'll just memorize the formula. And that was not the best way to go through all of my high school, undergrad, or whatever it was, right? I've learned in grad school, like, oh, you should know why these things are happening. It will help you, even though it might be hard. Okay. Oh, yeah, question?
Yeah, I like, I'm sorry, maybe somebody else had a question, but I liked how we did that with the Pythagorean identity. You if you're looking for like the tangent squared or something, you could just like divide like the sine by the cosine squared and so
Yes.
on,
Yes.
and just use that. You don't really need to know the other ones. And
Exactly.
yeah, I appreciate that.
Yeah, and that's why, I mean, sine squared plus cosine squared equals 1. That's
Mhm.
not hard to remember, or like,
Right.
It's relative, but we can remember that. And then when we just divide, how nice that we get the other ones. So it's like, and that's how they came up with them, right? Whereas like some students will, or even, I mean, even your professors, when they were students, like they'll all try to memorize everything, but it's like, whoa, slow your roll. Like even this, if you didn't remember the sine, oh, I shouldn't cover it in black, but if you didn't remember the sine of 2 theta, but you remembered for some reason the sine of u plus v,
Mhm.
you just change the u and the v to theta and theta, right? And we'll do the same with cosine. So let's check it out. So cosine of 2 theta, This, remember, we have cosine theta, cosine theta, which at first I thought to myself, why am I writing this? But yeah, this is right. It seems weird, but we'll make it nicer. And then sine changes. So it goes from plus to minus. And then we have sine theta, sine theta. And this is going to be, so this is where it gets a little bit weird, but this is cosine squared theta minus sine squared theta. Now, at first you think, oh, is this going to just be one? But no, it's one if you add them. So, so it's not one, but you can see below, and we'll kind of highlight this. You can take this and see below that we can actually get 3 different versions of this if we use that identity, which actually Michael just brought it up. So let's write it. Sine squared theta plus cosine squared theta equals 1. So from this identity, we can say, so if I replaced, if I subtract sine theta, so cosine squared theta equals 1 minus sine squared theta. If I do this, and then I substitute this guy in for cosine theta, I get 1 minus, I get this here. Then if I do the opposite, if I swap these, so I say sine squared theta is 1 minus cosine squared theta, and I substitute this in for here, I get 2 cosine squared theta minus 1. Now, maybe you just want to keep it at the original, like the original, we'll call this the OG cosine of 2 theta formula, right? Is this guy here, cosine squared minus sine squared. This is the good, this, this is it. But if for some reason you know what like cosine theta is, but you don't know sine or something, then you can kind of change it to make it nicer. Or maybe the problem wants it all in terms of sine or all in terms of cosine. You can do this with all of our identities. It's a bit wild, I'll say. And now let's look at, I think we're going to do like maybe two examples of this just to see, or 3, to see how we can apply this, right? Okay. So, and we're given this tangent, given tangent theta is -5/4 and sine is less than 0. So this means, okay, so the sine, remember sine is y. And so if that's negative, that means that the angle is somewhere here. So like my right triangle is like this, where my, oh, what am I saying? Sine is less than 0. Oh yeah, sorry, this is right. Because my y is negative here. So like this is the -5. So this would be theta, and my x is positive. Okay, so if I draw my right triangle here, it's going to be in quadrant 4. Okay. And we want to find these things based on our formula. Now, we will look at this and look at the formula above. But first, I do want to find this third side, this hypotenuse, because I know we're going to end up needing it, because whenever we do sine, like we'll need the hypotenuse, right? So let's just find this. So if we have, it'll be 4 squared plus 5 squared equals c squared. And so this is 16 plus 25, which is, so 41. Okay, so this isn't super nice, but this means that c is just going to be the square root of 41. We'll just leave it like that. That's perfectly fine. So square root of 41 is here. So whenever we're doing, sine or cosine in this triangle, we're going back to our right triangle trig, and we're good old SOHCAHTOA. It's never going to fail us, right? Okay. So now let's use our formulas. So from up top, sine of 2 theta, I'll use this here, 2 sine cosine. So this equals 2 sine theta cosine theta. And based on the given information, we can solve this, right? So remember SOHCAHTOA. I guess we don't need TOA technically right now. Or we did need it to write our triangle. So let's give it some props. So we want sine of theta, and again, I'm looking at this triangle, I'm looking at theta. My opposite side is -5. So I have -5, this is 2, we have -5 over square root of 41. Okay, opposite over hypotenuse. Then cosine is adjacent, so 4 over square root of 41. And look, we don't even have to rationalize. How fun is this? Because they already do it for us basically, right? So now we just multiply across the top. So I'm going to get 2 times -5 times 4, which will be -10 times 4, so -40. And then in the bottom, I just get 41 because square root of 41 times square root of 41. And if you wanted to see that, it's like this, right? Okay, maybe that helps, maybe it doesn't. But so our answer is just -40 over 41, which is pretty nice. Now we'll do this with cosine. So cosine of 2 theta, I'm going to use the main, I'm going to use this main formula here, right? So I'm going to use cosine squared theta minus sine squared. You could have used the others. You're going to get the same thing as me. I'm just using the -5 isn't positive. What? I'm not understanding. Is there a question? They tell us that the tangent is -5 over 4 and that it's in this quadrant. So that's how we know the 5, although like that's just how we know that is a negative number. I don't know if that's
Okay.
okay. Yeah, so this is given. It's because of this negative here. It has to go with either the 5 or the 4. And because sine is negative, it's going to go with the 5. Because if you think of tangent is sine over cosine. So they tell us, the reason they tell us this piece is to tell us which one, so -5 over 4, is to tell us like that this value is the one that's negative, not the 4. So hopefully that,
Okay.
okay.
Oh, okay, yeah, that makes sense now.
Okay, cool. Yeah. And if there's more, if there's questions more, please stop me. But okay, so now we're going to use our cool cosine squared theta here. And so my cosine, I already know what sine and cosine are from the previous problem. So my cosine was 4 over square root of 41. And remember, we're squaring all of this minus -5 over square root of 41. But we are squaring it, so that negative kind of becomes irrelevant. But this is going to be 4 squared is 16 over 41. And then minus 25 over 41. And so our final answer here is, okay, 16 minus 25 is -9 over 41. And so, okay, here's where Jakob's question from before kind of comes into play. You would think, okay, I see tan 2 theta. Should I use the formula for this? But for this one, I'm going to say don't use a tangent formula. Instead, and this is really just so we get used to sine and cosine. Instead, think of this as sine 2 theta over cosine 2 theta. And then we can, and here's the real kicker for you. We could do the formulas all over again, totally fine. Or look at what we found in A and B. So we could also take our answer from A, which was, the -40 over 41, and then just divide it, and maybe I'll do this, divide it by our answer in B, which was -9 over 41. And so if I write this is like -40 over 41 times the reciprocal. So I'll just write, and so these 41s will cancel, the negatives will become positive, and this just equals 40 over 9. And we don't need to simpler, that's simplified, so we're good. So now you could have, yeah, you don't need, exactly, no need to have the tangent. Granted, sure, like there's in the book, they'll probably go through it, but we're not going to come across anywhere that you would need the tangent. And in this case, when you have a problem, which I learned this way too late into grad school, and I don't know why, but almost always when you have a math problem and it has A, B, and C, unless I wrote it and I just wasn't thinking, you almost always like are going to use something, unless it's just, like if it was just A and B, they're just trying to get you to do sine and then cosine. But C, if there's that part C, a lot of times you're going to use the parts that you did before so that you're not repeating work. It's like your work, hard work is paying off, right? Yeah, very convenient, exactly. Yeah, which is cool. I mean, makes it more interesting, I guess. Makes you feel good. It makes me feel good, right? And in grad school, when I started to learn, like we would have problems, you know, that would go A, B, C, D, E, F. And I was like, why are there so many parts? But it was like, if you could do the first few parts, then it was all related. And the last 4 parts were easy. You know, if you got the hard parts, like in this case, A and B are the hard parts really to remember that formula and then plug it in. And then C, you're just putting in numbers and simplifying. So it pays off, but you know, it took me way too long to figure this out.
So for like homework / quiz /
Yeah.
test,
Yeah.
are you gonna want us to just probably dumb question, but are you gonna want us to like draw where it is in the quadrant, or you just want like the work?
Oh no. So if you do not, you totally do not need to draw the triangle. So if you just, I would want to see maybe this, right?
Okay.
Because I want to know like how the heck did you get square root of 41 if that's a right. But otherwise, yeah, this is not necessary, but it's just helpful. Yeah.
Okay. Thank you.
Yeah. Okay. All right. So last but not least here, we have another example, and then we'll talk a little bit more about, well, they're calling them power reducing and the half angle formulas, which half angle formulas for some reason, maybe they'll be my favorite teaching it again, but the double angle are always my favorite. They always take the priority, but maybe I got to give them a better chance. So we'll see. We'll see how we like them when we get there, right? But let's verify this one here. So again, we're going to use the our double angle here. Now something to note, and it's very important to be observant in these situations, which I typically am not, but we try. So I want to verify. And on the left-hand side, I see cosine 2x, so I could use the double angle formula, and then over sine, so maybe it'll simplify or something. But on the right-hand side, I see cosecant and sine. So here, I see no cosine of x on the right-hand side. So because there's no cosines, so I'm going to say use special form of cosine 2 theta. So just scrolling up real quick before I say which one. Going back to where cosine was all special and had like these 3, formulas, we're going to use, we see no cosine. So that means cosine we got to get rid of it. And so I'm going to look at this 1 minus 2 sine squared. That's what I'm going to use for this problem. And granted, you could do it the other way, but you'd end up replacing the cosine squared with 1 minus sine squared anyway, like in the future. So this is saving us a little time. Okay, so let's check it out. So we're going to start with the left-hand side, and my cosine of 2x is going to become, or maybe I'll rewrite it, cosine 2x over sine x. And this is going to become 1 minus 2 sine squared x. So I'm using the special form that I'm talking about is this right here, right? I'm using this. over sine x. And now, actually, maybe this will be prettier. Now I can remember my heart method, right? Okay. That's a really, maybe that's actually more normal because your heart is not like even, and I don't know. But there's my little heart method, right? And I'm going to get that this is going to be 1 over sine x minus, because that was a minus in there, 2 sine squared x over sine x. Okay, if I simplify this, I'm feeling good. We're going to get the right-hand side. So now I see cosecant x is 1 over sine minus, so one of these signs can cancel with the denominator, and I just get 2 sine x, and this is my right-hand side, and I'm happy to go. I verified. Okay, so before we get to the half angle formulas that are kind of my nightmare, I guess, because I like the double angle better. But before we get to that, we're going to talk about these power reducing. So basically, we know cosine of 2 theta or sine of 2 theta. We did these. But if we have something like cosine squared, is there a way, or we can rewrite a formula to get it so that there's no squared? So sometimes when you have a problem, you have like cosine squared or something squared, but you don't have like sine plus cosine, and you can't get rid of it, right? So you can always change everything to be cosine squared with our identity, and then we can use this fun formula here. And let's actually, I'll highlight. We can use this to solve for cosine squared. Okay. So, they're below, but we're just going to see how that happens. So from this, we would add 1 to both sides. We'd get cosine 2 theta plus 1 equals 2 cosine squared theta. Then we would divide everything by 2, right? And so we'd get cosine squared theta is going to equal cosine 2 theta plus 1 all over 2. And this is exactly, well, okay, so we spoiled it, but this is exactly what's here, right? Now, if you do this for sine, you would just replace the cosine squared with sine squared. And well, okay, and it's 1, okay, so if, let me actually write this. If we did this for sine, remember from up above, oh, and maybe I'll do it here. Remember cosine 2x is 1 minus sine squared, 2 sine squared. So this is also 1 minus 2 sine squared theta, right? And if you solve for this, so now what the way that we get this formula right here is by solving cosine 2 theta equals 1 minus 2 sine squared theta, solving for sine squared 2 theta, right? So you would subtract 1 from both sides. So you'd get, and maybe this isn't that great, cosine 2 theta minus 1 equals 2 sine, negative 2 sine squared theta. Then you divide everything by negative 2. So it ends up swapping, like everything's divided by negative. So then it's 1 minus cosine 2 theta over 2 equals sine squared theta. And that's how we get this here. Oh, and I should scroll down so you can see that better. I can show more work for that, but getting to the formula is not really the important part here, because these formulas are a bit more complicated. Like the double angle, it's good to know that. The sum and difference, you'll have to know those. These, I do think, and I'll double check. I do think we give you formulas, I know, like on the final. But I think for an exam with this, like if you needed something this kind of deep into it, like the half angle or the power reducing, if you needed that, the formula would be on the question for like a test. Except I did take all your tests because I finally wrote them. And on the top of my head, I just can't remember what we used. I think most of the time it uses the sine squared plus cosine squared equals 1. So, and the Pythagorean theorem, like stuff that you really are familiar with, but I will check for sure before your next test to see, what it does use, and make sure you know that, and know what you maybe have to memorize and what will be on there. Yeah, thank you, Miguel. I'm trying. Okay. So now we have, okay, so this was our power reducing, very minor, and they didn't even give an example here. So again, I don't know if that's on a homework, but problem, but if it is, at least you've got, we looked at it a little bit. Now we have these half angle formulas. Okay. And again, like I said, I shouldn't preface with they're not my favorite, but I did, so it's too late. But what I'm going to say about these, and maybe this is probably why these are used heavily in Calc 2. And I won't get more into it, but in undergrad, when I took Calc 2, like Calc 1, I was like, all right, cool, this is fun. Calc 2, it was a nightmare. And maybe it was the professor, but really it was also probably my theory of memorize everything. Yeah, spoiler alert, exactly, Michelle. Like, so if or when you get to Calc 2, this will be used, and you will be thinking, maybe you'll be thinking of me like, oh, she said it and I still don't like it either. No, just kidding. Okay. And they're not horrible. It's just kind of a lot. So half angle formulas, they're derived by these power reducing. So again, we're coming back to all the things we know, which the power reducing is derived from the double angle. So we all come back, it all comes full circle. It's like the merry-go-round, you keep coming around, keep going by. Do I teach Calc 2? I mean, I don't right now, maybe in a year, but I am taking next semester off of courses. So if you're hoping to have me, if you're taking Calc next and you're hoping, I am taking next semester off. I have 3 jobs right now, and this is just too much for me. So unfortunately, but yeah, but I will be back, and maybe they'll give me Calc 2. I can try to request it maybe. Okay. So we're substituting in, they're calling it alpha over 2 in for theta in that power reducing formula. So we're going to do this. And then, spoiler alert, like Michelle said, we're just full of spoiler alerts. They give you the formulas here nicely, but we're going to do this. Yeah. And Jakob, good luck. Exactly. To all of us. Right. Okay. So looking at this, we replace, every time I see theta, I'm going to replace it with this alpha over 2. So I'm going to rewrite this. So bear with. We have sine squared of alpha over 2. Right? And this is going to equal 1 minus cosine of 2 times alpha over 2, all divided by 2. Okay. So far, like, we're not so bad. We can simplify, like cancel out those 2's, right? Oops. We can do this. So it's just cosine of alpha, which that's nice. So I'm going to rewrite this. So sine squared alpha over 2 equals 1 minus cosine alpha all over 2. Okay. And then we have sine squared. So, if this was like x squared and we're solving for x, you just take the square root of both sides. We're back to basics here. However, when you do this square root, I should have done a different color. But when you do the square root of both sides, we've got to have the plus and minus here. We're not in the world anymore where we only get the positive. We need both. So this is maybe also like one of the other many reasons why I don't like this formula. It's just quite involved. But it is plus or minus the square root of this whole 1 plus cosine alpha over 2, right? And you can see if we, minus, oh my gosh, I already messed it up. Right, it's 1 minus cosine alpha over 2, because I got to be looking at this. So you can see that this here should match what we got, and it seems like it does. So good. Now, we aren't going to do this out for cosine, but you could just replace, you could do the same exact thing for cosine. And again, maybe this is a good spoiler alert. This is what you'll get, and don't worry about it. We'll trust that. And I can't take credit for these notes. Most of these notes are made by another professor at ACC because she's awesome. And so she like makes these notes and takes stuff from the book. And I mean, it's incredible. So I can't take all that credit. That helps me teach it okay, right? Or well. But yeah, so looking at this, there's our half angle. And then the last problem that we have here for today is asking us, I'm going to move my stuff up above, use a half angle or power reducing formula to find the exact value of sine 5 pi over 12. Okay, whoa. So first thing I'm going to do is, it said half angle or power reducing, but half angle, I already see like, okay, if I have 5 pi over 12, I know that if I take another angle and divide it by 2, I could probably get that. So let's try. So like 5 pi over 12, if I want this to equal alpha over 2, oh my gosh, why is there no 1 there? Okay, 5 pi over 12. If I want this to equal alpha over 2, I would just multiply both sides by 2. And this means alpha is going to be, well, 10 pi over 12, which is, wait, is that right? Yeah, 5 pi over 6. Yes. Sorry. 5 pi over 6, right? So I do know a little, so let's let our alpha equal 5 pi over 6, and I can use my half angle formula, that is this guy here, to get our answers, because, well, or answer, actually it's going to be answer, but we'll check it out. So let me write it again, sine 5 pi over 12. And we're going to think of this as sine of 5 pi over 6 over 2, right? Like alpha over 2, right? So now I'm going to, again, just like, I'm literally just going to copy and paste this bad boy formula right up here. I have plus or minus the square root of 1 minus cosine 5 pi over 6, all divided by 2. And okay, I do have to think a little bit here. 5 pi over 6. So I have to think, where am I going to do this? All right, maybe I'll write it up here. I have to think, so 6 pi over 6 is pi. So 5 pi over 6 is the one like right. So, you know, this is 5 pi over 6. 0, this is like 3 pi over 6. Okay, so it's in that second quadrant. So we're in quadrant 2. And the point there is negative root 3 over 2, 1/2. I mean, if you have to think about that longer, this is okay. But oh, okay. So yes, what you're saying, 5 pi over 12 is in quadrant 1, but I'm just talking about alpha for now. We will get to that, because first we want to focus on alpha. So this is alpha, but our theta equals the 5 pi over 12, alpha divided by 2. And when we divide that by 2, it does exactly what Jakob is saying here. When we divide it by 2, it'll take it somewhere here-ish, and this will be theta, and it will be in Q1, right? But it'll be, okay, my picture is so not to scale, so do not, but it'll be the answer that will tell us if it's positive or negative. But let me get back to, okay. So now I'm coming back to this here, and I'm gonna substitute in, I'm gonna substitute in my plus or minus square root 1 minus. So cosine 5 pi over 6, that was cosine 5 pi over 6. That's what I was doing over here. I was concerned about getting that. That's why we're in quadrant 2 for that. So cosine is negative root 3 over 2. So this is negative root 3 over 2, all divided by 2. And now I can kind of simplify this a bit. So this is plus or minus square root of 1 plus, well, okay. I'm going to do, okay. don't be mad about this. I'm going to do the heart method and get rid of this because I want to have one nice fraction inside there. I don't want to have something too crazy. But I'm going to do the heart method. So I have 1/2 and then minus a negative. So plus square root of 3 over 4 because 2 times 2 is 4. Then I can rewrite this inside. 1/2 is the same thing as 2/4, right? So this is like 2/4 plus square root of 3 over 4. So I can rewrite this as 2 plus square root of 3 all divided by 4. And then something kind of amazing is happening. If you're seeing it, great. If you're not, well, this is okay. When we have a square root and a fraction, technically it's the same thing as the square root of the numerator, 2 plus square root of 3, over the square root of the denominator. And square root of 4, that's pretty. That's just 2, right? So now I have plus or minus the square root of 2 plus square root of 3. Oh, not 2. All divided by 2. Okay. This answer, although it's crazy, and maybe this is, again, coming back to why I just don't like those half angle formulas, but this is an exact answer. But what we need to figure out is it the plus or minus? It's only the exact value of this is only going to be one of those. And so basically we have to figure out, this is sine, and we need to figure out which quadrant it's in, and is it positive or is it negative? Can you do square root 2 plus 3? No, because it's square root within a square root, right? So this extra square root was inside the original square root, and I can't just change that. Yeah. So, okay. I just want that to, I mean, I'm with you. Like, I wish I could, but yeah. Oh, can I scroll up? So see, the problem is I can't, because, I mean, I can hold it, but because I'm on the last, I should like add blank pages. Oh, I could probably, well, okay. I don't want to mess with this and delete anything, but I'll hold it. But maybe for the next notes, I'll add a blank page at the end so that I can scroll down and you can see, but maybe, yeah, that's okay. So, so back to what I was saying, we just want to figure out what quadrant this is in. Now, granted, even if you said, oh, alpha was in quadrant 2, in quadrant 2, you know, sine is positive, y is positive, but really it's in theta is in quadrant 1, sine is still positive. So in this case, it's positive. So even if you kind of mess that up, it would be positive, right? So our final answer to the exact value of sine of 5 pi over 12 is going to be, okay, how, I kind of want to get rid of some things. I'm just going to erase this and maybe rewrite it. So this is 2 over 4, 3 over 4. And so my final answer, and maybe I'll just write, and I'll hold this up in a sec so people can all see my scrunched up down here, is just the positive square root of 2 plus square root of 3 all divided by 2. And the reason for this, which I will write, is positive because theta equals 5 pi over 12 is in Q1. Okay, so hopefully that makes sense. If there's questions, please just let me know. Okay, and so if there aren't questions, this is sort of good, right? But so, and I bet you have to use this in some of your homework problems. I mean, I should know, I did do it last week. I'm trying to do all of your work a week ahead of you, but but like I said, the whole tangent thing, if that, I think we tried to stay away from those. If for some reason that was assigned in the book and it's too much, or you're really having trouble, just shoot me an email. And we can, what I will, at the end of the semester, well, first of all, we're going to drop multiple, homework, like your lowest two, I think, homework assignments or something. But also I can go back, and if I haven't already done this, people can remind me, oh, remember this homework assignment? It was like crazy or something happened. I can even just drop that one or give everyone 100 or whatever, however we do this, just to make it fair, because your homework grade shouldn't, if you're doing your homework, it should not be bringing your grade down, right? The point is to be learning, and doing homework is how you can learn, and being in class, I guess, as well. Okay, so let's try to save this so that I don't lose it.
Okay, wait, hang on. Just one other thought
Uh-huh.
on that
Yeah.
quadrant thing at the end that you're talking about. Okay, so,
Okay, wait, let me go back to it.
okay.
Oh my gosh.
Because sign can be positive if it's in quadrant 2, right? Because, the,
Oh, it is positive, right? So that's what I was saying. Like, regardless of whether you thought it was quadrant 2 or 1, I mean, sign was positive, right?
mhm,
Where if it was negative, it would mean that the angle, okay, maybe it was like 15 pi over 12, or maybe it was just something else, or 17 pi over 12. And when
mhm.
you drew it, maybe it ended up here somewhere, or here somewhere, right? And if that was the case, then that's where you'd have the negative part of this, right?
Then where the negative answer would apply.
Yeah, that's where this negative answer would apply.
Okay.
But because the original theta, which was just the 5 pi over 12, that is in quadrant 1, and that tells us that the sign there should be positive.
Okay.
Yeah, thanks. Okay, so a few things. We'll come back to what I said at the beginning. Book problems 6-1, they're due next Tuesday. 6-2, 6-3 due next Thursday. So don't stress. Quiz, it's short and sweet, I promise. It's on material from last week, so it's a throwback, maybe you'd say, or maybe even last Tuesdays. Yeah, it's a week ago. And it will open, I'm going to open it actually at 7:30, and I can, well, I need to leave by 7:40, but I will be ending class then, and you could even do it tonight and submit it. Or it is due Sunday for those of you that, you are like me and you do a million other things, or you just can't, you need a break from math class tonight, and you're going to do it over the weekend. That's perfectly fine. The other thing I wanted to say, my question of the day. So today it's going to be, what is your favorite holiday? I should ask this closer to the holidays, maybe, but to some holidays coming up. But you can say anything from, my neighbors, my dogs are afraid of all of their Halloween decorations, and it's pretty hilarious. So yeah, give me your favorite holiday, even if it's not an official one, or if you celebrate other, religious holidays that the US maybe doesn't, like, not everybody in the US celebrates, or whatever it is, right? Okay, let me figure out how to stop this.
Recording stopped.